Welcome to my second real-time sync talk. If you haven't seen the first one, who has seen the first one that I've done? Almost everybody. Awesome. I'll do a quick recap on that talk because it sort of talks about the internals of how the sync engine works. And this talk sort of is a continuation of that. I want to sort of go over sort of the challenges that we've had scaling the sync engine and how it actually works in the linear application, and what kind of changes we've made, and maybe how the API around it has formed because of these scaling challenges. To start things off with, we always want to build on strong foundations. That holds true for the sync engine. It was literally the first thing that I started working on when I started dabbling around with linear, now probably 5.5 years ago. And we sort of spent an outrageous amount of time building out the sync engine as a startup. And usually that's not something that any startup would usually do. Like you would want to build out product first in order to validate whether you're building something good. But our sort of idea always has been that we're not really building anything new. Like we know that the market exists and that there's millions and millions of users who use there you go, lost it for a while, who use issue tracking and project management. And the way for us to win is to just build something better, something that is 10x of the incumbent solutions out there. So we focused in the early days to make sure that we have a solid foundation to build upon. And one of those things was sort of the sync engine. And it took us a while to sort of get to understand really what the benefits were. Like we started out as thinking about sort of the user benefits that the user would get out of building the entire application on a real-time sync engine, which is obviously the real-time aspects of it. You immediately see any changes that other users make. Other things that we envisioned was that you would get performance out of the application because with sync you probably don't need to go to the network for every single page request and load more data, but you could store it locally and then simply access it and load it from the database or even have it in memory. And maybe the last thing that we figured is like if we store everything in the local database, maybe we can support offline capabilities as well. And that was pretty much sort of the benefits that are now evident today. I don't think any new benefits were added to the user side. But what sort of came as a surprise as we then went along and as we've built out linear in the past years is sort of the engineering benefits that have come out of it as well. The sync is literally at the core of the application, and it comes with I would at least say increased productivity for our engineers. The way to think about it is that you really don't need to think about networking anymore or some error handling scenarios. But much of the complexity of networked applications just taken care for you by the engine itself. If you want to sort of boil it down, like what you have as an engineer is an in-memory model graph or graph of data, and then you present that to the user and you modify it, and that's it. You don't really need to take care of anything else. The sync engine handles persisting that data, making sure that things are rolled back if in case the server doesn't accept those changes. Or making sure that changes are offline if there's no network connectivity, that transactions are queued up when we want to send them out. It makes sure that if you have in-flight changes to your data model and somebody else makes changes at the same time, that your changes are rebased on top of theirs, and all these small things that otherwise you would have to implement on a case-by-case basis and for every single feature over and over again. I don't know how much of a saving that is. To me, it feels like we can be 2 times more powerful because of this, and we can just ship functionality and features much quicker. The other interesting benefit was that we don't really need any servers. Well, any. We don't need so many servers to run the entire application. And this took us a while to sort of realize that it's very resource. Well, what is the opposite of? It doesn't use many resources on the server side because the clients essentially load up the entire state of the application locally. There are no page requests, or there are no requests to the server for every single page load. Only mutations, only changes in data require network requests. So when a client refreshes their page, in a perfect scenario, we don't make any network requests. We do make a few, but not too many. So there's not much load on the server when the user uses the application, which means that we probably can run the entire linear application on the back end with 10 times less servers than other applications which would sort of have some sort of network request for every single page load. So that's a few of the benefits, and this is the slide that I shared as the end result of my last sync talk, sort of detailing the internals of sync. I'll do a quick recap. If you are sort of more interested in how this works, you should definitely go back to my previous talk and have a look. But in the internals of it, what you have is effectively an object pool of model objects that somehow get loaded up into the client, either from sort of your local storage or from the network. Somehow from the sort of backend database, and you've got this big blob and big pool of just individual objects that have properties on them. So in our use case, you would have like organization, you would have multiple teams, you would have multiple issues, and you would have multiple users, all sort of randomly in one big pool. What the sync engine then does with this, and over time as well, it tries to sort of build this object graph out of that big pool of objects. If you have, for example, an issue will have a property pointing to the team that the issue is associated with, and the sync engine will take that information and then reconstruct a nicely usable object graph out of that data. So what you'll in the end get after this construction has been completed, you will have an object at the root, or a model object at the root, which is your organization. We call it organization. It's actually a workspace. We just can't rename our models at this point anymore. Like we have committed to talking about organizations when we actually mean workspaces. And an organization will have a collection of teams, and those teams in your object pool will have been hosted into that collection. So you can access the collection of teams, which will contain all the teams in that object pool. Each team again will have a collection of issues, which contains all the issues for that team, and those again are hosted. So what you end up using as an engineer is not the object pool, but you get this nice object graph out of it. And we use MobX to tie our interface and our UI to those model objects in that graph. So whenever you access a model object, we make it observable using MobX. And then when you render your view and access properties on individual model objects, MobX will note that there's sort of a correlation between your view and that model object, and when that model object in any way updates, or actually when individual properties on that model object updates, that's a note for MobX to re-render the view that was sort of dependent on that model object. So effectively, when you render your views, they will automatically stay up to date without you literally doing anything. There's an observable function that you need to wrap your component in, but that's literally all you need to do in order to make your view stay up to date with all the changes in the model in the object graph. And that holds true for any real-time changes as well. The nice thing about this is that the sync engine doesn't care where those changes come from. Like if you make changes as a local user to any of the model objects, they will automatically be reflected in your UI. All the associated components will be re-rendered. If you have iterated over a list of issues, that list of issues will be re-rendered, and you see your new issues. But the same holds true if somebody sends an update from the network. Like if another user makes a change, That change will make its way into the sort of object pool, and then it will be hoisted into that object graph. And again, automatically your UI updates. So it's effectively sort of a local change to your data is the same as a network change to your data. And you do need to do absolutely zero in order to support that. You just render your view and all is good. Some other pieces that are important in sort of the internal workings of the sync engine is the transaction queue. So when you then start making changes to the model objects, what you literally do is you have your local model objects in memory. You make changes to their properties, which are automatically reflected in the UI because of our binding. And when you then call save on that model object, the sync engine will look at that object, be like, well, you changed these 3 properties. So let me create a transaction out of that and add it to the queue. The queue is also persisted on local disk. So in case you're offline, we can replay those changes on top of your object pool and load them up again. So if you refresh your page, we will continue retrying those transactions. But over some course of time, those will be sent out as network requests. Like they actually will be batched up to make it a bit more optimal. If you make changes to 10 model objects at the same time, those will all be batched up into a nice GraphQL mutation and sent to the backend. The backend then will do whatever it does in order to validate that those changes are good. The backend might make other changes as well, like it might execute some workflows in order to sort of change other model objects that are affected by the change that the user just made. And then somehow through this sync resolver in this slide, the changes will be then broadcast back to all the clients. All the clients in that organization are connected to that sync resolver. It's actually no longer a sync resolver. This was 4 years ago when it was called that. It's essentially just a sync server. And all the changes will be broadcast to all the clients connected to that organization. They will be received, mapped into the object pool, or properties will be updated, new objects will be inserted, and saved locally on the user's disk.
Also the client that made the change initially?
Also the client that made the change initially. I can come back to sort of the life cycle of a transaction in a later slide. We can look at how that happens. But that is sort of a very brief overview on how the sync engine works internally. For the remainder of the talk, what we can do is we can not look at sort of whatever is on the right-hand side of things, because this is what you as a user essentially see from the sync engine. You see an object graph that is somehow kept in sync with all the changes that users have. And then you have your view that is essentially a representation of that object graph. And because the view is a function of the object graph, we can also sort of forget about it for the rest of the talk. You just need to know that if the object graph changes, your view automatically is kept up to date as well with those changes. And I want to sort of dive deep into how we initially built out the pipeline for making these changes and keeping the clients in sync, what problems we uncovered, where we hit performance problems, and how we solved them. So really what a sync engine does is just 2 things. It gets the client up to speed, and then it keeps the client in sync with all the changes. Super simple. There's not too much in it. So let's start off with essentially the first implementation that we had for our sync engine. This is all that there really was to it. We had, whoops, not there yet. We had the object graph on the left, and let's say we have a new user coming in, and the user doesn't have any local data in the local database. What we do is we make a request to a GraphQL API to load all the data. You literally say hey, I'm a user, here's my credentials, here's my user ID, please give me all the data for that organization. And the GraphQL API will be like, okay, let me go to the database, let me construct queries to fetch all the data that is visible to you, and let me package it up in a big JSON blob and stringify it and send it back to the client. The client will receive it, unpack it, construct model objects out of all the objects contained in that what we call a full bootstrap, and then construct that object graph from it. And then it will write it or flush it down into IndexedDB. That is sort of the getting up to speed part of sync. It has some problems. We'll get to them soon because we run into them pretty quickly. But getting up to speed is essentially going to the backend and loading up everything that the client can have, storing it locally on disk. And the next step is then to keep in sync. Like once you have loaded all that data, you need to somehow, you don't want to load up all the data every single time. Again, like you want to get delta updates of all the changes that happen in your workspace. So what you then do is, as a client, we make a WebSocket connection to a sync server, and then the sync server starts getting updates to the user. And to answer the question, like how do transactions flow in the system? The client will also use the same GraphQL API to make changes to its objects. And when a client makes a change, it will not store it immediately in the local database because that change hasn't been verified yet. Like it's not truthful. It's an optimistic change that the client has made. We do update the UI for that on the client because we want to immediately react to any changes that the user makes. But we won't touch the local database yet because we don't know if that change will be accepted. So we make it in memory, that change. We construct a transaction, send it to the GraphQL API.
But the transaction is stored.
The transaction itself is stored on the client in a local database, yes. So the client will store it in a local database so that it can replay it in case the client refreshes. But it's just a queue of transactions which are essentially loaded up into memory when the client comes back online. And then one by one, the client will try to send them to the GraphQL API. And the GraphQL API, when it receives it, it can either accept it or reject it. Rejection is pretty simple. You had some sort of validation error, like essentially we made a mistake, like it is on us to make sure that the client changes or the changes that a user can make in the client will be accepted by the backend because we work with optimistic updates. We make sure to validate the data on the client side because we immediately show those changes to the user. There are certain cases where that is not true, where there might be a clash with the data. Somebody might have updated data in a way where now your change is invalid. In that case, the server will reject that change, and the sync client will then roll back those changes in memory to the user. So as a user, it will look like you made a change, you see the UI updating, and then 500 milliseconds later, it will revert itself back to what it was, and you have the option to then sort of opt into showing an error dialog. I think we show it by default, like if something goes wrong, we try to present a user presentable error sent by the backend, and that shows up as a toast to let the user know that something went wrong and the changes that they made have been rolled back. And the transaction queue will just make one request at a time for those transactions, and then replay those changes onto Postgres. Now, the GraphQL API, as it writes those changes into the Postgres database, which means they're now committed, they're now part of the truth, they will also write a what we call sync action to a specific table in that database. And a sync action is just a record of change to the data set of a workspace. It will have the model's ID, it will have the changed properties, it will have indication on who made that change and what kind of changes it is. It might be an insert, a deletion, an archival, or an update. And then it's the role of the sync server to go to that table and constantly read on it. The sync server will always sort of read from the end of that sync actions table, read anything that is newly added to it, figure out like what clients are connected to that one particular sync server, go through that list and distribute those sync actions to the corresponding clients based on whether they have access to that data or not. And that's how, through the WebSocket, then the clients will receive updates in real time, using the socket server. And at that point, when they receive those updates through the socket server, is when they also get written to the disk of the client. So nothing gets written until you receive it essentially through the sync server, in order to make sure that you don't write anything that might actually be rolled back, or if you refresh at the correct time, that you don't get out of sync. So if you've kicked off a transaction, for example, and that is in flight, so you've sent it already to the server, and now you refresh your client, what will happen is you will still have the transaction in your local database, because we haven't yet seen a response to it. It will have been applied on the backend, because the backend received that request. It will have saved it to the local database and written it to the sync action table. And now that when your client refreshes, it essentially will have a conflict, which we deal with. We will be listening in on the sync updates we get from the server before we start sending transactions. And we do have a deduper in there where the transaction log that we had on disk will check if the transaction ID matches with what we got from the socket server. If we already were able to save the transactions that we had to the backend. That's not always the case. It might happen that we send it twice, which is perfectly fine. Like, it's just another update with essentially the same properties. So even in case if we sent the same update twice, nothing would happen. Like, it would not be a non-change. Nothing would be written. The only thing that will happen is if you, for example, delete an object or delete an issue, for example. You might get 2 deletions, the second one of which would fail with an error because the object already has been deleted. So we try to detect those conflicts in case users refresh at the correct time. But even if you can't dedupe them correctly, it's not a biggie. The user might see just a quick error toast, which might be a bit weird, but given that you just made a change and then refreshed, maybe it's fine as well. So second time the user starts up and loads up the client, we don't need to go to the server anymore. Like, we have everything stored locally in the database, and we have an up-to-date representation of that data in the database because we've been listening on all changes on the WebSocket. So what we do is we read from the local database. It's a bit hard to see here, but essentially we do have a specific database in IndexedDB called linear databases. It will contain essentially a list of all the databases that the user has at some point created. We might have multiple databases because we might have multiple workspaces that we're associated with, or multiple even users on that same computer. So a database name contains a huge hash that is constructed out of multiple things. That it will have your client ID in there. It will have the organization ID is sort of unique. Well, the client ID is unique to the organization ID, so we don't need to add the organization ID in there. But we will also have a version hash of the database defined by us. Like, if we for some reason need to nuke the entire database, we just increment this version number, and that then will generate a very different hash for the database. So the client will be like, well, I don't find that database, so let's reconstruct the database from scratch. And then it will contain a number of sort of other metadata related to the database in that field. But the client will construct this hash. It will then check the linear database to figure out whether there's an existing database. And then if it finds one, it will use that database with the appropriate hash and read data from it. And that database contains tables for every single type of model object. In this case, I have no idea what data this is or what model object. We just hash the model name. But it will contain essentially one or more key paths, which we can use to query that data. The ID is always a key path, so you can always query by the UUID of a model object. And then the value will be just a JSON blob of the data or the serialized data of that model object, essentially containing all the properties in JSON serial format. There also is a specific sort of metadata and transactions table. Transaction, you can imagine what goes in there. Obviously, transactions will be written into that table. And the metadata will contain metadata information about that database. It will contain things like the last sync ID that I've seen and written to the database. And that's a concept that we have throughout in sync. All the sync actions will have an incrementing ID going into from 0 to forever. And each client will know which number it has seen in that sequence. It will say, well, I've received a sync packet with an ID of 57, so I know that I don't need to care about anything that came before 57 because everything's written into the database already. And that is also being used in the next step, which will come to soon, to sort of let the server know what the client actually has seen already. It will also contain sort of fields on what model objects we've loaded. It might be, for example, that you load up in one sort of session, you load up all the data from full bootstrap, and everything's nicely persisted in the local database, meaning that the persisted flag is set to true on that model object. But then an engineer makes a change to, for example, the issues model. They add a property. Now that model object is invalid. It will contain more data, and the client's data should be deleted and reloaded. And we use the persisted flag in here to indicate that that's the case. So the next time the client then refreshes, they will loop through all the tables and figure out their hashes, which are stored as essentially the table name for those model objects. And we'll figure out, well, the issue hash doesn't match anymore. Like I don't have a table for the issue. It will then go into the method table and say, persisted equals false to indicate that, oh, we need to load up persistence data and we need to wait for that. And we'll then load up, data for just that one particular table. So do what we call a partial bootstrap for the data. But maybe I'm getting ahead of myself because, that came later. That's the way how you sort of keep the schema changes in sync between the clients. So we're pretty, simple with handling schema changes. We simply delete all the data that is part of a schema change. Which is maybe something to think about when you make changes. Like you want to make bigger changes in one go. You don't want to sort of do it on Monday, Tuesday, Wednesday, and Thursday, because that will invalidate a lot of data, and clients will have to wait a bit longer before they see anything when that happens. And maybe we could be smarter about this, but I haven't really seen a case where this would help much with performance. So to get back to like the first implementation of sync as it stood for literally one day, and then we found that it's a bit problematic. We need to add something else in there, and what we needed to add is delta sync. So we do have a problem with the previous slide, which means that when we do a full bootstrap, we will load up all the data from a specific time time in history, and then we will connect to the WebSocket. Any amount of time might happen in between. Like your network might be slow. It might take like 5 seconds to load up all that data. And 5 seconds later, you connect with the WebSocket. Somebody might have made changes in the meantime. And the way the sync server works is that it doesn't know about history. Like it just continues forward. When it sees a new sync packet, it will send that out to all the connected clients and get over it and continue. So what we needed is a way for clients, like once they've loaded up all of the data, or when they come back with a refresh, to sort of quickly catch up, not with a full bootstrap, but with a delta bootstrap. Like they want to see all the changes that have happened, in the meantime, while they were offline, or since they did their bootstrap, whatever that time is, they need to catch up with all the changes. So what the client will do is they will take that last sync ID that they had stored in the database, and send it to the sync server, saying, I need all the data since the sync ID, like, send it all to me. And the sync server will be like, okay, you're requesting all the data since sync ID, 3000. I know that I have sync data until the sync ID 5000, so let me query the database for all the changes for your organization, and I'll send you a big blob of data. It's essentially fast forwarding the client to that state. And after that, the client can receive sync updates, and the client is now in sync with the rest of the world. Small problem. The sync server started effectively sort of burning out and becoming very, very slow, crashing, and all of that. What we sort of didn't, in the first implementation anticipate, and I think this implementation lasted maybe for a few months or so, is that delta syncs can be pretty heavy. Like a client can come back, a week later, and a lot of changes might have happened since then. Like if you have an active organization with, say 500 users, and you come back a week later, there will be tens of thousands of changes to each model object. And that means tens of thousands of full changes to model objects being serialized as JSON and sent out when a client connects. And the way the sync server works, because it wants to be in real time, it wants to work through these things. Whenever a new client connected, what it would do, it would pause everybody else's updates and service that one client saying, oh, you need a delta sync, so let me fetch everything. Let me then package it up, send it to you, and then I'll continue my process because now you're in sync. And now I can continue my process of reading sync actions and sending them to everybody so that everybody is in sync. If it had continued to send those sync actions, you would have a problem on sort of the client side of things. And the code would just be much more complicated because you would have this one client that we haven't sent the sync actions yet because they're still receiving the delta sync. Everybody else does, and now I need to memorize all the sync actions that I've gotten since then, and it would just be convoluted. So the way we then fix this is, well, let's not have the sync server be involved in sending those sync delta packets, but let's just GraphQL. We have a nice API. We've got multiple of pods running on the back end. Why not just make a request to the server, the GraphQL server, because it's super reliant and it can just infinitely scale. There's sort of no state involved in the GraphQL API. So the delta sync is made to the GraphQL API. Now we do have. Yes. So we still have one problem, which is we need to add this small piece in here. We need to add a queue. Again, to overcome race conditions, like when the client connects, you might be receiving already sync actions before you get your delta update. And then you might be writing things to your local disk in the incorrect order and overwrite more recent changes. So with a queue, what we now do is the process of getting up to date and then staying in sync is the client will load up all data from the backend as a full bootstrap. It will then connect the WebSocket to the sync server. It will start receiving synced updates, but queue them all in memory. It won't apply them anywhere. It will just keep on adding them to this local queue. While that's happening, it will then make another request to the GraphQL API saying, please give me a delta sync up until whatever the sync server told me was the last sync ID, because that's what I need. I've seen everything else, and I'm keeping that queue up and running, but I need that delta in order to catch up to whatever the sync server has started sending me. We receive that from the GraphQL API, we apply it to the local database, then we flush the queue to the local database, and now we're real time. Now every single sync update that we get from the sync server will be applied in real time to the local database. And everything's fine. So, and this was probably the diagram that we used for probably the first year or so. And then we started growing. And as you grow, fun things happen. So the first problem that we run into was, man, Bootstrap is taking ages on the client. Unexpected. Like I would have thought that the GraphQL API is something that would be hit first. But we actually started seeing that it's a bit slow to sort of launch the client when you have a lot of data. And super annoying. I don't really want to sort of wait ages for a normal refresh. And the reason for this was simply, if you load up all the data in your local database, that might be on a big organization like 80,000 or 100,000 individual model objects. You load them up from disk, which is relatively fast, but then you construct them into objects and you add MobX on top of that, and that is actually pretty slow. So we need to change, a few things. So the first thing that we did was we came up with what we now call partial partial bootstrap. So we say, we no longer like really need to load up everything from the local database, but we can wait on some of the stuff. Like it doesn't have to be all loaded in time. And the way, like the reasoning here was that if you look at the application, like you have certain model objects like comments and issue history that are not really shown in the application until you get to a certain screen. Like comments and issue history are only shown when you look at an issue, an individual issue. And most of the time users start with the active issues or my issues screen. So we don't really need to sort of bootstrap all of these objects necessarily. So how do we do that? Because on the client side, like we need to implement something in order to then dynamically load these model objects when needed. And it's not really a, well, like we don't want to make it more complex for the engineers than needed. We want to make sure that you don't really have to change anything how you use the structured data in order for us to optimize how we load up the client. So the way internally, the collections work is that you will have a team which will have a property called, for example, issues, which will be a collection. And from the get-go, we created this our own class to hold collections because we anticipated that we will have to, at some point, optimize how we access those collections, and we want to be in control of what happens when a user or when an engineer accesses that collection. In the early days, like your tree would already sort of have all the data in those collections. So a team would have all the issues. A team would have all the issues, and an issue would have all the comments associated with it, because we would load up everything from the local database. Now we wanted to delay that, and we want to make it lazy. So what we introduced was a lazy collection, which is a subclass of the collection. It works in the same way. As an engineer, you don't really need to know which one you're accessing. It has the same accessors to sort of get all the elements of that collection or find things in the collection. And we simply said, well, let's start easy. Let's start just with the comments and issue history, and let's make the comments collection on the issue lazy loaded. And what that means is if you access comments, like if you in code, you access the property of team or issue.comments, the sync engine will notice. It's a getter, and it will know that, oh, okay, so you now want to sort of access the elements of that collection. Let me check if they're actually loaded. And if not, let me then actually go quickly to the database and load them up. So what will then happen is, if they are not loaded, which they are not when you start the application, we will go to NextDB, load them up, populate them, and then get back to the user. So how could we do this without making any changes to how you access the data structure? Because in the first time they don't exist, and then they do exist. It's not really any different from somebody updating a collection. Like the first time you access the collection as an engineer, you will get 0 elements back. You'll get an empty array if you access the elements of that collection. But then, like a millisecond later, you'll get another update saying, there's now data in there, which looks like somebody updating them through the network, for example, or you making changes yourself. So when they are hydrated into the collection, again, MobX will kick off. Hey, this collection changed, and any UI that access that collection will re-render, and you will now see those elements in that collection. Which, if you don't do anything else, it will work. So eventually, and very quickly, you will get those comments in an issue, but there's still a flash. Like there's still 2 renders for any section that show comments. You will first see no comments, and then immediately later, you'll see some comments. And we do have tooling to get over that, so you can. If you know that a collection is lazy, you can kick off hydration beforehand, or you can wait for hydration to happen. And hydration generally means sort of going at this point to the local database. In the future, it might be going to the network as well. But it means that you get a promise back And when that is fulfilled, then you know that everything's hydrated. So what we do in code is we add suspense boundaries around anything that we sort of lazy load. We don't need to show a spinner, but what we do want to do is like nicely fade it very quickly in when that happens. So we don't want to render a view where you don't see any comments, because that might mean displaying the text no comments, for example. So we want to not render anything while the hydration happens. And when that promise then resolves, the suspense boundary will re-render that component and be quickly faded in, nicely rendered with all the comments in place. So that's why when you sort of very quickly, like if you're super fast and you go to an issue and go to the section, you will see the comments fade in that section. We also do sort of all this hydration beforehand. So when you roll over a list component in an issue, we already kick off that hydration because we anticipate that the user might be clicking on that element. So when they then do, the comments are already there, so we can immediately render them. We don't need to fade anything in. And if this, when this was correctly implemented, like there would be no discernible change to the user UI, and the user wouldn't really see anything. What they would see is that suddenly we bootstrap much faster. So that's what we did with the first bottleneck fix. We implemented partial bootstrap from the local database. The other thing that we did was just optimize how we serialize MobX on those model objects. Because as I said, that is a very slow operation. It takes time to make an object observable. And previously we would do it for all the model objects. And now we actually do it only when we access those model objects. So when we find them by ID, for example, or when we access a collection, that's when we create or make them observable, which made it much faster to bootstrap as well. So yeah, next problem. The bootstrap itself, when we load up everything, is quite slow. So we fix it for a local database, and then obviously move the problem to the next bottleneck, which was the GraphQL API is actually pretty slow at doing things. Well, we already have the ability to sort of delay things loading up from local disk, so we don't really need to load up everything in one go. So what we then did is we added a delayed bootstrap to the startup sequence. So we do a main bootstrap, which is loading up most of the models, like everything that is important, like teams, organizations, users, issues, whatever is usually rendered at the first time. But we moved everything else into delayed bootstrap. What went in there was, I think, comments and issue history in the beginning. Again, those are models that are, they're plentiful. There are very many issue history elements, like probably 10 per issue, so they're super heavy. And just delaying loading of that and rendering the UI before we even get to load up the comments made things much faster. So now bootstrap was fast again, and we want to get to UI very quickly and then catch up with whatever the user has. So with the way this works with those lazy collections is that we just added quick check into the lazy collection saying, if you don't see them in the local database, we might actually be still bootstrapping them. So the call to load them delayed might still be ongoing. So let's wait for that. So the promise wouldn't fire until we've actually loaded up the delayed bootstraps, and then we would go to the IndexedDB and check, what do we have as comments and issue history for this. And that made things, a lot faster, probably like, 5 times faster bootstrap to get down with. Well, then we move the problem just to the next place. So the next problem that we started having was that the GraphQL API started not being slow, but crashing. And we were a bit dumbfounded at first, but then quickly realized that we were just running out of memory. And the reason for this was GraphQL is good for small operations, but it's really, really bad for huge operations. Because the way GraphQL works is before it can send anything to the client, it needs to sort of have constructed the entire response locally in memory. It cannot stream anything. It's a JSON blob, and the response is a big JSON blob, and you need to have all the data present before you can construct that response and send it to the client. So the way the graphical bootstrap would work is it would go to the database, it would load up everything from the user, it will have that data then in memory. It would then construct essentially the graphical response, which is a big JSON serialization of all that data, and it would have that data now twice in memory. And it would then send it to the user while keeping all of that in memory. And once the user had received the entire blob, which might take a long time because networking is slow, that's when those big memory blobs were effectively removed. So if you loaded up a data set of 50 megabytes, which is fine, like compressed, that's much less, but I think that even the linear workspace today uncompressed might be something like 150 megabytes. You would have to keep that all in memory for one single bootstrap request. So if you make, 20 bootstrap requests at the same time, you run out of memory because we've set the limit at 2 gigabytes of memory for our pods. So not very good. So we need to find a solution to this. And what we did is we introduced a new thing. We introduced the streaming REST endpoint. So GraphQL can't do streaming, REST can. So we added a new endpoint that is sort of internal to us. It's not public facing. And only the client uses it. And what it will do is the client will make, instead of going to the GraphQL API, it will now make the same request to the streaming REST endpoint. The streaming REST endpoint will create a streaming database connection to the database with the big query. There is one big, huge query that contains everything that is needed in order to load all the data for that user from the database. It will then stream the response row by row from the database to the API and then immediately send it over to the client. So it won't really need much memory. If the client is fast, it will essentially read a few rows at a time, keep in memory, because then it sends to the client and the client accepts them, so they can be removed from memory. In order to account for sort of slower clients, because what might happen is your database, we want to load stuff from the database as quickly as possible in order to keep the connection count low. So we might load up a lot of stuff from the database and have everything in memory. Because the client is slow, we're not able to send it as quickly to the client, so we have to, again, keep stuff in memory. So what we added in there is to write things to disk in certain cases. So we receive it from the database. If we go over a certain watermark in our memory, we start streaming them to disk, and from disk we stream them to the client back. And that led us to not only be sort of have the ability to service more clients, but also be faster. I don't remember how much of an improvement that was in terms of speed, but it was substantial, and it was much faster to do a full bootstrap with. So nice. We're in a place, a pretty good place. Everything is going well. And then, if you saw how that flame has moved around, obviously we've now fixed the streaming REST endpoint, and then the flame reaches the Postgres database itself, because we've just moved sort of load over to the next place in time. So the problem here was that those bootstraps were becoming very hard on the database. We had no problems catching up with mutations and all the changes that clients were making, but clients were making full bootstrap requests pretty often, and we were increasing our user counts. So the database started sort of just going nuts. We increased the size of the database to a huge one, and still sort of had problems with it. So the first obvious choice is to just read from the read replica. We don't need to read from the main database, but we can go to the read replica for those full bootstrap requests. Not as simple as it sounds, because the read replica can be a bit late to the party. It can have lag, even if you run a huge query on the replica, it can be out of sync by as much as 10 minutes. So we need to figure out how the client knows what it has loaded and account for that in the delta sync. So it became a bit more complicated, where full bootstrap would now have to tell the client okay, you got everything, but only up until this delta or until this sync ID. So when you do your delta sync, load up from there. Not too bad, worked out for some time, but then again the read replica wasn't able to handle all the load, and we were in certain cases still going to the main database. and we wanted to sort of find a better solution. Not that the database was on fire anymore, but it was slow. Like it started getting slower and slower doing these huge queries. A relational database is great for certain cases to load up everything that goes into a huge organization. That's what a relational database is not good for. So what do you do? Then you add a cache. And what we started doing is adding a new database, a Mongo database in there. We tried a few things. We tried a side-by-side a Mongo approach and Bigtable with GCP. And it turns out that Mongo was actually quite a bit faster than Bigtable from Google. So we still are running on Mongo. And what we do is we periodically save all the data in a specific serialized format to Mongo. So we take organization by organization. We go, I think every single day we go through the entire, through all orgs, or we might be more smart about that nowadays, where we only do it if necessary, like if the organization has enough changes. That's when we sort of do this big dump. We take all the model objects for all the users, we serialize them nicely and put them all next to each other in the database so that reads are super fast. And instead of streaming from the Postgres database, we stream from that MongoDB. And again, the MongoDB, it is a bit older, the data, like it's not up to date, but we have all the mechanisms in place for the client to actually catch up with that data. So the data that we write into that MongoDB will also contain like the last sync ID at which it was generated, and then the client can catch up with Delta Sync. Alex. Well, no, it's not always from MongoDB. So the streaming endpoint will make a distinction between like where to go to, and it's quite complicated. What it will do is like to simplify it, like it will check if there's a valid valid dump in MongoDB, and if it's not too old, then it will go there. If there's no dump, it will do it from Postgres, but at the same time will generate that dump. I'm not exactly sure like whether we ever wait for the dump to be generated and read from there. There might be something where we wait like for 5 seconds and then try to read the dump. If not, then we just go to the main database. It's a bit more complicated. It's all in code, but in the end, like we make the best possible distinction of where to load that data from, and it's all sort of abstracted away. Like you don't need to really care where it's coming from. Delta sync in this graph always goes to Postgres. Yeah. It's no, sorry. So we moved Delta sync to the streaming REST endpoint as well. So and that goes to Postgres. Yes. Yeah. We played around with going to the read replica as well, but Delta sync needs to be real time, so it's much more complicated than. I think we had something in place where we would read from both the replica and the main database, like from the replica, the bulk of it, and then everything else from the main database. But we've got some new things coming on that front as well. So the next problem, finally Postgres done, backend, all cool. The streaming REST endpoint is a bit slow again on the client. God damn it. We're loading up a lot of data. Even with sort of our delayed sync and all of that, it's still a lot of data to load, tons of megabytes for large organization specifically. Like I think our organization, even though it's pretty big, it's still working nicely and fine, and takes a few seconds, 3-4 seconds to load all the data set. But when you get to sort of larger growth organizations, definitely not up to par. Like we want to be faster at loading up that full bootstrap. So what can you do? Like, turns out we have essentially all the mechanisms, under the hood already in place in order to do something, really nice and smart and cool. And that's actually what we're working on today. Hopefully, getting this out there. I don't want to make any promises anymore because we've pushed the boundary back so often. It's a hugely complex task. But what we're doing is we add a batch loader in between. And the best way to describe, sort of a batch loader in this diagram is that we do a partial bootstrap when we load up the client's data, and we load up only the absolutely necessary data. The data that every client will see on every single page, on the first page, or the data that doesn't have tens of thousands of entities, and that essentially includes organization, teams, users, no longer issues, no longer attachments, obviously not comments and issue history items, and there might be others as well that we don't load, and everything else is essentially pushed to the partial or to the batch loader. And the best way to describe a batch loader is essentially a way to stream data in on demand from the network. To quickly describe what that sort of means, let's go back to this graph that we had earlier when we did lazy collections, and let's look at the teams now. So now we do have a team that no longer has issues. So if you see, if you go to a team page with active issues, the first render will be that you get an empty list of issues, which was previously the case as well, because we already had moved sort of issue loading to be lazy, but it would always load them from disk, because that was sort of the next way to make things faster at Bootstrap on the client side. But now we might not even have those things on disk. So what we're saying is, as part of full Bootstrap, we're no longer loading any issues. We just get rid of them. Same goes for attachments. So how do we deal with this? So again, you come in and you touch the issues of a user or the issues of a team, and what the system will try to do, it will, as lazy collections do, they will go to the IndexedDB and they will try to load up all the data from the local disk. But there might be a case where there is no data in the local disk, and we have quite a few mechanisms in order to figure out whether there's data or whether there is not data. It's complex. I don't want to go into the details, but it uses what we call partial index values. We know if we have loaded up all the issues, for example, for a user or for a team or for the entire organization, and we write those to disk as well. So we can ask the disk whether we've actually even loaded up these models. And if we haven't, we will actually, the collection itself will make a call to the batch loader and ask sort of the API to fulfill that request. It will go to the streaming endpoint saying, oh, hey, I'm looking at issues for this team. Please give me all the issues for this team. And the streaming endpoint will gladly give them all the issues. And they will then be stored into the local database. And then obviously the clients will be fulfilled as well. And now suddenly you have all the issues for the team and the user. The reason we call it batch loader is because it does batch loading. The first problem that we saw with this, our first implementation was simply when somebody requests anything, just make a network request, load it up. Then we were looking at the first list of issues, and every single issue can have an attachment, and it can have multiple attachments, and every the attachment property is a collection, and it's obviously empty. And we don't know if it's loaded or not. So we actually have to touch it because the issue will display, the issue row in a list will display attachments, GitHub requests, pull requests that have been associated with the issue. So every issue row that we render, we will touch the attachments collection to see if, are there any attachments in this collection? All the attachments are partially loaded, which means that we will make network requests for every single one. And suddenly you look at one view and you get 50 network requests being sent out individually. Those come back all saying, no attachments here. So what we created is a batch loader, which will, over time, for 50 milliseconds, get all the requests in, figure out what is being requested, give back a promise for each of these requests, then batch them up. It will do awesome things like sort of deduping those requests, grouping them together, even in the future, optimizing them. Like if you're asking for, attachments for, 50 issues in one go, maybe it's easier to just load up all the attachments for that team that the issues are involved in. So we can do, be smart about this as well. And anything else in the interface that, touches any of these lazy models will essentially be batched together. And the batch loader will take up all these requests, dedupe them, make sure to figure out like what the optimal requests are that we can send to the backend, combine them all into one, and then make one single network request. And the backend streaming endpoint will sort of, look at the request and fulfill it. There might be multiple database queries that the backend does, but there's only one single network request that goes out. We'll get a bunch of models back, all sort of mishmashed, together. And once we've received them, we can tell all the requestees that they've now been fulfilled. Like all the collections that they wanted to populate have now been populated, so they can go about their own way. Suspense boundaries will be lifted, and UI will render again. And that's our way to get this working at scale. Yes, Alex.
Does it mean we should use more suspense boundaries now and just prevent multiple renders of the components?
Yes and no. So the way we've set it up for now, and we're still working on this, is to have suspense boundaries in very certain places and make sure that we do kickoff hydration before you even get to some place. For example, like when you look at a team, we will kick off, we will ask the batch loader to load up all the issues and attachments for that team. I can't answer the question because I actually don't know the answer for. What happens in code, there's been multiple things that will now ask for issues. You will access the team's issues, which will kick off a request. Then you will have some requests that will ask for the issues and attachments to be loaded using partial load, because that is faster. We can go to the cache with that. And then the batch loader will look at both of these requests, be like, well, this partial batch load fulfills also this request, so I can throw out this request. I only need to do this in order to fulfill all the requests. So there's a lot of deduping going on. You don't really need to care. You just request whatever you want, and you'll get it in an optimized way. And all of this was required in order to make the use case of loading issues from the network possible. But the beautiful thing is that again, nothing in code changed. You already had your collections, be lazy. They would previously be loaded from local disk, and now they're just, might be loaded from the network. Will take a bit longer, but from a engineering standpoint or code standpoint, nothing has changed. It's still the same request that you do.
Now it's longer, right?
For the user, it's definitely longer. Yes. We'll have to see. I think our suspense boundaries do have a loader after 4 seconds, but we're not really hitting that. We want to keep every load still sort of under 500 milliseconds or a second, depending obviously on the load of the user. And we might do optimizations where we not load all the issues, but start streaming them in or whatnot. But that's where we are. And to sort of quickly jump into some code to sort of demonstrate the APIs around this lazy loading, because they become more important. This is a super simplified model of an issue. It has an ID property. It has a parent, an optional parent, and it might have children. So we have sub-issues which are represented in code as, with the children property, and a parent would be if you're a child, your parent will point to the parent issue. Now, this is how it would look like if the issue wasn't lazy loaded, if the issue would always be in memory. And the changes that we need to do in order to support lazy loading, not only network lazy loading, but also lazy loading from InDexDB, is the ones in yellow. So suddenly your parent actually becomes the cached promise. And a cached promise is our implementation of essentially a promise with one additional thing. It has a value property that you can read. If it has been fulfilled, the value property will be set. If it hasn't, it won't be set. So if you're trying to access it, you don't know if it's being set, it's perfectly fine to just access the value, just make that accessor optional. And again, MobX will make sure that your component gets re-rendered if that is ever fulfilled. You might get a small flash, obviously, because the loading might take time. Or you can definitely check and make sure that you resolve that promise, in which case what you get back is a hydrated version of that parent. So we do have another sort of method that we added, which is the hydrate method, which will return you a promise of a hydrated issue. And literally what that means, like this is all TypeScript stuff. Like there's nothing inherently, like no objects involved that changes. Like when you call hydrate, it's effectively at runtime, what you get back is a promise. But we type it to be a promise of a hydrated issue. And hydrated is a definition that we have done here, rather hard to read. But what it literally does, it goes through your objects, looks at every single property. If it is a cached promise, and if it is, it will set the value to be non-optional. So the value is set after it has been hydrated. And that's how we do sort of type-safe accessors for these validating functions. Again, you have two options. You can either just call the value and either get it back or not. You have to make it optional at that point, or you can specifically say, hey, I really want to hydrate this thing, and then I get back a hydrated object. And a hydrated object also will have all your collections be hydrated at the same time, but because collections don't really change in their behavior, like they'll either be empty if they're not hydrated, or they will contain items if they are. We don't need to make any changes to the interface for those collections.